Hi, good afternoon. I'm Christopher Spell, and today I'm going to be giving a presentation that's an overview of pipe stress analysis. So today we're going to be discussing what is pipe stress analysis. We're going to give an overview of the process of completing an analysis of a stress system. And then at the end, we're going to present a little case study of actually completing a stress analysis so you can get a good idea of how it works from beginning to end. So what is pipe stress analysis? It's basically a mathematical method to analyze the stresses that are going to be present in process pipe and the mechanical equipment that's involved with that pipe. So you're going to basically say, if I fill this pipe up with hot process, how's it going to behave, and does that behavior cause stresses that are greater than what's allowed under the ASME code B31.3. They used to do pipe stress by hand, with hand calculations, but now it's mostly done with computer programs, and we're able to be much more precise with it that way. So what causes pipe stress? One thing is temperature. Obviously, if you get things hot, they want to expand, and pipe that is routed in a certain way that tries to expand is going to resist that expansion, and the resistance causes stress within the pipe. Pressure can cause pipe stress, not to the same degree as temperature, but it does contribute to pipe stress. The weight of the pipe and the valves and the fittings that are on the pipe can cause pipe stress. If you have a long run of pipe that spans too great a distance, then it's gonna, we've all seen a moment in shear diagram. The long distance is gonna cause a bending moment in the pipe, and that could cause stress that's greater than is allowed. And then you also have occasional factors that lead to pipe stress, such as wind. There's earthquake codes in the ASME codes, and then mechanical vibration and things like that. Wind is the largest occasional factor that plays into pipe stress. Okay, so a little bit about ASME B31.3, the American Society of Mechanical Engineers. B31.3 is the section of the code that covers pressurized process pipe. So that's any of your pipe that's out in a chemical plant or oil and gas refinery. And we also use different sections of the ASME code. If you have a pressure vessel, then you're going to use a different section of the code, or other equipment requires different codes from within ASME. Okay, so a little bit about the process of analyzing a stress system. So these are the steps, and then we'll go into a little more detail about those steps after we've overviewed them. So you're going to receive a stress package from your project manager. You're going to build the model in a computer program that's able to run pipe stress. Specifically today, we're going to talk about Caesar 2 because that's what I'm familiar with. So you receive the stress package, you use that package to build your model. You have Caesar run an analysis on that model. It runs computer modeling almost like an FEA to analyze every piece of the pipe. After you run it, you're going to address any overstress areas. If there's any failures due to stress, you're going to analyze the results and see how you can fix any issues. And then you're going to compile your results into a report that can be submitted to the project engineers and the pipe designers and civil engineers and structural guys. Okay, so you're going to receive a stress package, and in that stress package, it's going to hopefully contain some reference documents pertaining to your stress system. And when I say stress system, that's just an area in a plant or refinery that needs to be analyzed for stress under ASME. So you're going to get a package, and it's going to have these documents in it. Hopefully, it's going to have a P&ID. And a P&ID is a document that has all of the equipment, the valves, the pressure vessels. This here, a tank. So you have equipment, vessels, valves. You have electrical lines and signals running in there, but none of it has any dimensions. It's just basically a flow diagram of what equipment should be contained within this system. That way, if you see coming off of this tank, there should be two lines with a valve each, and then a jump over with a valve in between them. If you look at your ISOs, your isometric drawings, then you should see that equipment on there. Along with your P&IDs, you should also receive a line list, and a line list is just basically spreadsheet printout that has each line in your system printed out. And a line, if a system is a section of pipe, then a line is just a smaller subdivision of that system. It's going to be a run of pipe that's, from one place to another. And it's going to have each line listed, and then it's going to have the process conditions for those lines. So you're going to have temperature, pressure, if the line's insulated, where it's coming from, where it's going to, the line size, the thickness, and things like that. In addition to the line list, you hope your package has piping isometric drawings, or as we call them, ISOs. And you can see an example of that down here. And a piping ISO is basically the next step from a PNID. So a PNID has all of your equipment shown and represented, and then your ISO is going to show the actual layout of the pipe in the site. So you're going to have all the same equipment, and it's broken down into smaller little drawings, but it's going to have dimensions, so you know how things actually relate to each other, and you can use these ISOs to actually build a realistic model of what that pipe looks like on site, so that then you can analyze it and be confident that you're running a realistic analysis. In addition to just having dimensions and pipe, you also have a bill of materials on your ISO drawing, and that just has all of the materials that are contained in this drawing. You've got pipe, elbows, welds, fittings, flanges, and any other thing like that that's contained on the drawing. You're going to have it listed and itemized over on the bill of materials. And then normally on an ISO you'll have, again, process data for that specific line, and that spool of pipe is going to be listed at the bottom, so you just redundancy, you can easily find your process data. In your stress package, you're also going to want to find pipe spec, and that is a document that comes from the client that has listed all of it. So any pipe that falls under this spec, it will list for this size of pipe it has to be this thick, and for these flanges they have to be this size, and things like that. So it's more data to build a more realistic model and make sure that your model is accurate. And then if your system contains any mechanical equipment like a pump or a pressure vessel, then you're going to want to have equipment data sheets and equipment general arrangement drawings, so that you can see what that equipment actually looks like, and you know what size it is and how it relates to the system around it. Okay, so after you get your stress package, you're going to come into your computer program, Caesar 2, and it's a stress analysis program, and this is what the hub looks like. And you can see it's got a lot of toolbars around here. You can do a lot with it. This is where you actually build your model of the pipe, and you can select which icons are shown, and it would take a whole additional presentation just to go over each one of these toolbars and what they do. So we'll stay surface level and just say that when you open up Caesar, this is what you're going to see. And if you're familiar with FEA programs or anything like that, a modeling program, this looks familiar. You build your model, and then you have different ways to manipulate it and things like that. So we're going to come into Caesar 2. When you first start a model, you're going to see your input screen here, and this is where you set all of your parameters, and then you actually build your model and you input dimensions. So first thing you want to do is set your temperatures and pressures, your operating temperature and your design temperature, and your pressures as well. You're going to select your material, and then Caesar propagates these modulus values for you, and some other material properties. You're going to specify other things like insulation, diameter and thickness, and then the fluid density, so that it can calculate weight when you run it, because different fluids, obviously, depending on their density, are going to weigh more when they're filled up inside of a pipe. Okay, then your next step is to look at your ISOs and build your model. You're going to start from the beginning, and you're going to step by step using these options here. You can go in the Y, Z, or X direction and build your pipe out, run it along, turn it. You can add bends, you can add reducers if your pipe changes size on the ISO. You can add a rigid, which is a valve or a flange or some other rigid element such as that has weight but not a whole lot of flexibility. you can add restraints, which are your supports, steel supports, and guides, stops, things like that, and we'll get into what those are later. And so this is everything you need to build your model right here. So after you set your parameters, you go and you build your model, and then you have to specify to Caesar what load cases you want it to look at. So a load case, it may be difficult to see, but you set a load case that say you want to look at what happens when it's just the weight of the pipe. If it's empty and you just want to see what the weight of the pipe does, because sometimes you have a system out there that's empty. So you specify that load case. You say, okay, so what does it do when we fill it up with hot process? And so that's another load case. Okay, well, what do we do if the wind starts blowing hard? That's another load case. What do we do if the temperature fluctuates? It goes from this temperature to that temperature. That's another load case. So that you set your load cases, and Caesar's going to run stress calculations for each one of these load cases, and it's going to iterate thousands of times for each one, basically like an FEA for each individual element that you build in the model. So after you've got your model built, and you have your parameters set, and you tell it what load cases you want it to run, then all that's left to do is just run. You tell Caesar, okay, run your analysis, and it starts to iterate. And after, only a minute or so, it'll kick you out to the output screen, the results screen. So this screen shows you your results. Here's a list of all the load cases that you told it to run, and as you can see, they're all black, which is good. That means that you didn't have anything that was overstressed. All the stresses present in that pipe are under what's allowed by ASME. So this is what happens with a good system. So it's well designed, it passes stress, Caesar says everything's good. You may do a little bit of investigation to make sure that, say you go to a restraint summary and you ensure that none of those supports are carrying a crazy amount of weight. And then once you see that every load case passes, then you're satisfied, and you compile your results into a report, and then you ship your report to the people that are concerned with it. Now unfortunately that's only probably about half of the systems pass right off the bat. Normally there's one or two issues that need to be addressed within a pipe system. So if you run your stress analysis and Caesar returns a red load case, that's no good. That means you have a stress in your pipe somewhere under those load conditions that is greater than is allowed. So in this case, it's our job now to go find out where our overstressed point is, what's causing it, and how we can fix it. Okay, so we do that by coming up here to the output icon, and it allows us to see what our pipe is doing under that load condition. So let's go over what we're looking at here. This red area that's highlighted red there is actually the location of our overstress point. So as we can see, it's at a base support where it's welded to an elbow. So that's a lot of bending pipe there, and that's a very common place to see overstresses. And the gold design there is actually what the pipe looks like whenever it heats up and it's under that operating condition. So this is the way that it deflects when you submit it to those loading conditions. As we can see, it's wanting to bow out this way, which tells us that there's probably something up in the pipe this way that's rolling. Something back that way is growing too much and causing this pipe to roll, and we end up with an overstress here. So then we say, okay, what can we do to fix that? And we're going to look at the key to finding a solution for these stress systems is, how do I change the system as little as possible? So if I can add one support in a location, that's a small change. And if that fixes the problem, then that's what I'm going to go with. I'm going to start off with small changes, maybe add a support or restraint. And if that doesn't work, then you're going to have to get into your more complicated redesigns of your piping systems, and you're going to have to reroute your pipe a different way that mitigates those stress issues. So the few of the ways that you may correct a pipe stress problem is with supports. You always go to supports first. So if a pipe is on a shoe like this, Then one type of support you can add is a guide. And a guide goes on either side, it's depicted here. It goes on either side of the shoe, and it prevents that pipe from moving side to side. So that is used a lot of times in a long run of pipe. If the wind case is too strong, that pipe starts to edge to the side, you can put a guide on it and it will stop that movement. Another type of support is a stop. Now it's not shown here, but where it would go is on the front and back of this support, and it would stop this pipe from moving forward and backwards. So these are just ways to prevent the pipe from doing things that are harming the pipe. In addition to adding these supports, they can have gaps in between the pipe and the restraint so that you allow a little bit of movement, but not as much as there would be without the restraint. Okay, so after you correct your stress system, you've made the necessary corrections and additions, you're going to compile your report that's going to get sent to the people that are in charge of designing it and building it. So your report is the complete story of the stress system. You have to compile documents from your stress package. So all of those documents we talked about earlier, that tells people how you built your model. You have to assume that the person reading your report has no knowledge of this system. So you're going to tell them how you built your model. And that's what your ISOs and your P&IDs are for. And then you're going to print out your results, which are things like a stress report that tells where the highest stress point is in each load case, and a restraint report, which tells you that none of these supports are carrying too great of a load for what they're meant for. And it's always important, each conclusion that you draw in your report has to be backed up by documentation, so that if someone says, well, how did you figure that out? They can flip to a different page in the report and there's their answer. So that's how you hope pipe stress systems go, but it's not always that smooth. Like I said, if you can't fix a system by adding a support or a restraint, then you have to redesign the pipe, and pipe designers don't like to hear that. And you have to collaborate with them to find out what's best for this system. There are going to be pitfalls that you run into with structural limitations. And so those are things that you have to work towards together to figure out. And then your worst case scenario is you're modeling a system and you want to include existing pipe that's already on site so that you can make your model more realistic. And when you model that existing pipe, you find that there's a problem in pipe that's already out there in the field. And then you have to tell the client there's a stress issue in existing pipe, and that turns into a fiasco. So. All right, now a quick case study on how this process goes from start to finish. So this is a stress system that was run several months ago. As you can see, it's a little complicated. It's a little more complicated than the one that was shown earlier. We actually have a pump here. This is the suction and discharge nozzle of our pumps. And our system is strictly this pipe running from the pump, and it comes up here and runs into a pressure vessel there. All the rest of this is existing pipe that just happens to interface with our pipe. So in order to get a realistic picture of what our pipe is doing, we have to include all this to see how it affects our pipe. So after we built our model and we tell Caesar to run it, we look at the nozzle loads on the pump, because each pump has a vendor allowable nozzle load. On each nozzle can only carry so much load. And we see here with the red values that we're over those allowable loads. So we come and we look at our pipe and we see here's our nozzle, and we have a long run of pipe going into a set of flanges that's actually an inline strainer, which is pretty heavy, and then another long run of pipe before we finally get to a support. So basically the problem is we have all of this weight being held up by our support on one side and our pump nozzle on the other side. So that's where our load comes into play, because it's actually being used as a support. So what we want to do is add a support between this heavy set of flanges and our nozzle. The only problem is structural engineers and the client don't want any steel underneath this pipe because it's too close to the pump. It's going to impede access to the pump. So the solution we come up with is a spring hanger, a variable spring hanger. There's existing steel above this pipe that we can hang a spring down from, and it will remove the load from this nozzle. And as we can see, that reduces the load to quantities that are allowable according to this pump vendor. Okay, so a short review of what we've covered today. Pipe stress analysis is just a mathematical method of analyzing the thermal and other stresses involved in process piping. We're beholden to ASME B313 and other client standards are secondary there. The analysis process is you receive documents, you build your model, you run the analysis through the computer, you investigate and analyze the results. If changes need to be made, you make those changes and correct any stress issues. And then once you get all that done, you compile your report. Thank you, and if you have any questions, you can submit them in the comments below.